She is a PhD candidate from Cairo University. She's doing it in the Electrical and Communication Engineering department. And her interests are in the area of networks on chip modeling, optimization, process variability. So we're going to look at interesting aspects of link level design and variability-tolerant NoC link design. This is the topic of today's presentation. And then it's interesting that she has worked in industry for 10 years as a communications engineer. So we have a very experienced engineer here. That's the speaker. Right, so we need to connect, I suppose. So nice picture here. Yes, good. Thanks, Ray. Okay, so, Eman, you talk now.
Good afternoon, everyone. First, I would like to thank Mr. Moon, the conference chairman, for his extreme help for me to get the visa of trying to be here with you today. I'm really thankful for you, and I'm very happy to be with you here today. Second, I would like to thank my supervisor. I have two supervisors, Muhammad El-Kharashi from Ain Shams University and Muhammad Fathi Abuelyazeed from Cairo University. Today, I will talk to you about variability-tolerant NoC link design. The presentation outline, first I will talk about the objective of my work, then what is the contribution of this paper. A quick introduction about network on chip will be here, then I will go to the link level, how I model the link delay, how I take variation random and systematic into effect, how I use those components to calculate statistical delay, and how I use the statistical delay to make a design methodology for NoC link. Then I will show a case study, results, and conclusion. Before I go to the objective, I will talk about variability-tolerant NoC link. The variability I mean process variability. CMOS fabrication process are mainly front-end and back-end. The front-end processes are those involved in the fabrication of the device. The back-end are those involved in the fabrication of the interconnect. As technology scales down, the fabrication process make components not as we designed. There is variability. This variability will change the electrical component of the devices and the interconnect, and in sequence will affect the delay. It will be compared. The work in this paper has two objectives. The first objective is to meet the delay constraint of the link, of the network link, taking variability effects into consideration. The second objective will be, as we are working on statistical delay, not on the worst case delay, the power cost will be less. That's why we are actually saving power. So we are having two objectives, variability tolerant and power efficient at the same time. I have mentioned 3 contributions for this work. The first contribution, I have a model that takes the floor plane of the design and gets the delay of each NoC link in the delay in the floor plane. And it also calculates the systematic and random deviation component of the delay of this NoC. This is the second contribution. I use those 2 components to design the link with optimum number of buffers and their. You all know about network on chip, and it's the optimum solution for their optimized electrical properties. There are several topologies used, Tour mesh stars. In our work we use mesh. In this topology, here is the link. Here we focus to study the variability effect on the links. Circuits represent switches. We don't study the variability effect on switches on this field. On the circuit level, the link is considered as a driver and repeater with a wire that has interconnect resistance and capacitance. On the layout level, each interconnect can be considered as signal carrying conductor and the ground plane. Between the signal carrying conductor and the ground plane, there will be signal capacitance, plane to plane capacitance or interlayer capacitance, coupling capacitance, and fringing capacitance. Those capacitance will affect the delay. Actually, also the dimension of the wire, the line width, the line thickness, the spacing between the line wire will also affect the delay, as shown by those equations. The total interconnect capacitance composed of interlayer fringing and coupling depend on the dimension, THW. The resistance depends on T and W. The delay depends on the interconnect capacitance, interconnect resistance, the load capacitance, CL, and the load, the driver resistance are transistors. So the problem is variability in the fabrication process will make variability in the dimension. Variability in the dimension will make variability in the capacitance and resistance. Variability in the capacitance and resistance will make variability in the delay. That's how we take variability into consideration. Random variation. By random variation, I mean it's completely random. It doesn't depend where the link in the die. It can be anywhere, and its effect is random. Random variability arises from fabrication processes like random dopant fluctuation in the doping processes, oxide thickness fluctuation, and line edge roughness. We compute random effects in threshold voltage, gate length, oxide thickness, and line widths using Hessian function. Actually, we use several inputs. The threshold voltage and the gate length will have some deviation with a mean and standard deviation. These values are reported in the ITRS thresholds. Okay? We use the Hessian function that use the delay equation, and we substitute for dimension and threshold voltage, and the Hessian function uses the random standard deviation for the inputs to get the standard deviation of the output. So if the delay is a function of R and C, which in turn is function of W and H and V threshold and L, if we have as an input to Hessian the standard deviation for the input variable, Hessian will give us the standard deviation of the delay. And if the standard deviation of the inputs is random, the calculated component is the random component of the delay. The systematic variation is different. The systematic variation depends on the location of the link. So if we consider the mesh to be in 2G plane, systematic variation says that for any parameter, there is a correlation between the value for the parameter at this point and the value on the parameter at the other point. It depends on the spherical length between the 2 points, so we use this equation. It depends only on the standard deviation of the parameter we are investigating. So for this threshold, for example, we have the original value for this threshold E, and we know it's a standard deviation. We can calculate this threshold at this point, and this point, and this point, using the polar distance between the origin and each point. this wheel, we have a variation map for this section. If we are using, we get variation map for gate length, and we get a variation map for oxide thickness, and we get a variation map for line width. If we superimpose these variation maps on the NoC floor plane, we will get the delay of each link depending on where it is on the die. So at this position, we have a value for this region, LG, W, and Tox. We use it to calculate the delay at this point, and at this link, and at this link, and at this link. And then we calculate the deviation of different delay values across the node. Thus, we give a systematic component with mean and standard deviation for the delay. Okay. The total deviation in the delay will be the sum of the random component and the systematic component. This slide shows some results. We compare our work to the work in 6. Here, at different technology, 56, 46, 5, 45, 32, 22 technology. This is the random component of the delay. It's 35%, 37%, 43, 34. This is the systematic component of the delay, and this is the total component. As we can see from the graph, as technology scale down from 56 nanometer to 22 nanometer, the systematic and random and total deviation in the delay increase. Then we make some statistical analysis and we get random and systematic component of the delay, so we get statistical delay. We use this in the design. How? Our design methodology depends on, I have a floor plan for NoC describing the XY position, height and length information of each link. I have process variability parameters mentioning the mean and standard deviation for threshold voltage and gate length and oxide thickness from ITRS report. I calculate the systematic and random component of the delay, using them to calculate the optimum number of repeaters and cell size for NoC link. So I have two, the NoC link for each component, as we saw in previous slide, and the optimum number of repeater and cell gain, as will be seen in the case study. So if we calculated statistical component of the delay, depending on interconnect capacitance and load capacitance and transistor resistance and interconnect resistance, we will have equation of the delay. This equation has N and H. So he's using statistical value for capacitance and resistance. With constraint for the delay, we can select optimum N and H. We use the case study for 4x4 mesh. We calculated the nominal value for N and H of each link without considering any process variability in the effect. Then we take process variability in the effect. The difference between the NH process making statistical analysis and NH product in the nominal value will give us the power cost to tolerate the process variability effect. The result shows that for our case study, the total power cost will be 11%. But if we compare statistical analysis to the worst case, we will see that we will be saving power. Our power saved in the case study is 28%. This is the result. We study 4x4 NoC at different technology for delay constraint 0.2 nanosecond. As we can see, as the technology scales down, the cost to tolerate process variability increase from 6 to 9%. So to conclude, as technology scale down, delay variation increase to reach 10%. Using our variability tolerant NoC design will make us tolerate the delay at the power cost up to 33%. Yet our design methodology take more power less than the worst case. It was saving 28% in the case of 4x4 NEC at 45 nanometer technology. If we ignore the NoC link variability, the design may not meet the design constraint, so it will fail. But predicting the variation and taking it into consideration will make the design work and save power at the same time. That's the end of my presentation. So, any question?
Questions, please? I'd like to ask you about the actual tolerance of variability. So this is quite analytical approach. So you analyze the effect of variability here. But in terms of the actual design, what would you do to somehow tolerate this variation?
It is actually designed for each technology. There is ITRS report that gives technology parameter deviation, sigma, this region.
Yes, that's technology parameter deviation.
So I use this technology parameter to calculate the statistical delay.
So but the actual designing of the electronic circuits, I mean, do you have some work done together with this analysis, which basically tolerates variability?
For
links.
My case study for 4
So do you use, what kind of techniques do you use for link design? Do you use asynchronous techniques, or you have some form of tuning clock in connection with the data about variability? I'm just interested what kind of design, actual circuit design techniques that you apply.
I didn't use the clock, actually I use the delay constraint. 0.2 nanoseconds, it can be changed. If you want to change the clock, you will change the delay constraint. So whatever the clock, you will just change the delay constraint.
So you, by taking into account the knowledge that variation is not the worst case, yeah?
Yes, it's not.
But according to what you have, so basically what you do is just you reduce the clock period, yeah?
Yes.
Rather than accounting for the worst case, yeah?
Yes.
Right, okay. So, because I mean, I was slightly misled by the title of the presentation, that the actual circuit design somehow deals with variability. The actual circuit itself. Okay, but it's input. Okay, I think we can explain. So in terms of power consumption, so these are all delay constraints. Yeah. So
the power consumption is proportional to the number of repeaters and their delay. Using statistical delay, we will define the number of stages.
Requirement for repeaters.
Yes, and these requirements are less than worst case.
Yeah.
That's why it's made power saving.
So through that you have power savings. Okay. Yeah. Thank you. So, any more questions, please? Well, if there are no more questions, again, thank you very much.